Hello everyone and welcome. Today we are going to explore one of the most fascinating technologies shaping our world, lasers and optical sensors. From smartphones and medical imaging to autonomous vehicles, modern society increasingly depends on the ability to generate, manipulate and detect light. We'll start with the physics of light and semiconductors, moving to how lasers generate coherent light, and then explore how sensors capture photons and transform them into electrical signals. So let's begin. At the heart of both lasers and sensors lies a single physical process. The interaction between light and electrons inside a semiconductor material. Everything begins with something called an electron-hole pair. When a photon, which is simply a particle of light, strikes a semiconductor, it can transfer its energy to an electron. That electron absorbs energy and jumps into a higher energy state, leaving behind an empty position called a hole. This simple event can lead to three completely different outcomes. The first is detection. A photon enters the material, creates an electron-hole pair, and the resulting electrical signal can be measured. This is the operating principle behind the CMOS cameras, photodiodes, and many optical sensors. The second process is spontaneous emission. Here, the excited electron eventually falls back down and releases its energy as a new photon. Because this happens randomly, the emitted light is incoherent and spreads in many directions. This is how LEDs and OLEDs displayed work. The third process is the most important for lasers, stimulated emission. In this case, an incoming photon triggers an excited electron to release another photon that is perfectly synchronized. Same wavelength, same phase, same direction. This process creates coherent light, the defining characteristics of lasers. So, in a way, lasers and sensors are opposites. Sensors convert light into electricity, lasers convert electricity into a highly controlled light. This slide summarizes the three core optoelectronic processes. Detection absorbs photons, emission generates photons, amplification multiplies photons. What makes semiconductor technology so powerful is that the same physical platform can perform all three functions. That's why the semiconductors became the foundation of modern photonics. By engineering materials carefully, scientists can decide whether a device behaves like a detector, an LED, or a laser. This ability to control light at the microscopic level changed telecommunications, computing, medicine, manufacturing, and consumer electronics forever. Now let's talk about one of the most important concepts in semiconductor physics, the bandgap. Not all semiconductor materials behave the same way. Some materials are extremely good at emitting light, others are extremely good at detecting light. The difference comes down to whether the material has a direct or indirect bandgap. In direct gap materials like gallium arsenide, electrons can release energy directly as a photon. This process is very efficient. That's why direct gap materials are ideal for LEDs and laser diodes. Indirect gap materials like silicon behave differently. In silicon, electrons cannot easily emit photons because momentum must also be conserved. This requires interaction with a vibration in the crystal lattice called a phonon. That extra requirement makes light emission extremely unlikely. For silicon, it's terrible for lasers and LEDs. But interestingly, silicon is excellent for photodetectors and electronics. And that's why modern computers rely heavily on silicon electronics while many lasers rely on materials like gallium arsenide. Lasers come in many different architectures depending on the application. At the top we see VCSELs, vertical cavity surface emitting lasers. These are compact lasers that emit light vertically from the surface of the chip. They produce only a few milliwatts of power, but they offer excellent beam quality and can be manufactured in massive arrays. VCSELs are widely used in smartphones, facial recognition systems, optical communication, and data centers. Next are wide stripe lasers. These sacrifice beam quality in exchange of raw optical power. Then we move into laser bars and arrays. These combine many emitters together and can generate tens or even hundreds of watts. Finally, at the highest scale, we have the stacked laser arrays capable of producing kilowatts of optical power. These are often used to pump solid-state lasers like neodymium YAG, systems used in industrial cutting, welding, medical systems, and defense applications. So laser engineering is always a balance between three things: power, beam quality, and efficiency. Different applications prioritize different trade-offs. To understand laser deeply, we need to think about light from a quantum perspective. Light is not just a wave. It also behaves like a discrete packets of energy called photons. Atoms contain electrons occupying specific energy levels. An electron can move between these levels only by absorbing or emitting a photon with exactly the right energy. This process creates spectral lines, unique optical fingerprints for every atom. That's why astronomers can determine the composition of distant stars. By analyzing the wavelengths of emitted light, they identified which atoms are present. In photonics, controlling these energy transitions allow us to engineering LEDs, lasers, and optical sensors. The following diagram represents how energy moves inside atoms and molecules. The S states are singlet states. The T states are triplet states. When a material absorbs light, electrons jump into excited states. From there, several things can happen. They can release energy rapidly as a fluorescence, they can lose energy through vibration and heat, or they can transition into triplet states and release energy more slowly through phosphorescence. These processes are fundamental in chemistry, biology, imaging, OLED displays, fluorescent materials, and quantum optics. The key idea is this: once matter absorbs light, many pathways become possible, and engineering those pathways is the essence of photonics. Now we move deeper into the semiconductor physics. Electrons inside an atom do not move freely. They exist in regions called potential wells. In isolated atoms, electrons occupy discrete energy levels, but when atoms are brought together into a solid crystal, their energy levels begin to interacting. The result is the formation of energy bands. This transition from isolated atomic states to collective energy bands is one of the most important concepts in solid-state physics. It explains why solids can behave as metals, semiconductors, or insulators, and ultimately it explains why modern electronics and photonics are even possible. In a periodic crystal structure, electrons experience repeating atomic potentials. Instead of isolated energy levels, we obtain allowed energy bands separated by forbidden regions called band gaps. The valence band contains electrons bound to the atoms. The conduction band contains electrons free to move through the material. The band gap is the energy difference between these two bands. This gap determines nearly every electronic and optical property of the material. A small gap leads to conductive behavior. A large gap leads to insulating behavior. An intermediate gap creates a semiconductor. This is the foundation of all modern electronics and optoelectronics. The electronic structure of a material depends strongly on the atoms that compose it. Here we compare carbon and silicon. Even though they belong to the same family in the periodic table, their electronic behavior differs dramatically. The arrangement of orbitals and the spacing between atoms determine how energy bands form. These microscopic quantum properties ultimately control microscopic behavior. Whether a material behaves like a metal, semiconductor, or insulator depends on how electrons are allowed to move through those energy bands. This is why material engineering is so important in photonics. By changing composition, structure, and doping, engineers can tune optical and electrical properties very precisely. Now let's compare the three major classes of materials. Metals contains huge numbers of free electrons and essentially no band gap. That's why electricity flows easily through copper or aluminum. Insulators are the opposite. Their band gaps are so large that electrons cannot move freely under normal conditions. Materials like glass or ceramics behave this way. Semiconductors exist in the middle. Their conductivity can be controlled. By adding dopants, changing temperature, or applying electric fields, we can manipulate the number of free carriers. This controllability is what makes semiconductors revolutionary. They can behave like conductors or insulators depending on how we engineer them, and this flexibility enables transistors, sensors, LEDs, solar cells, and lasers. Temperature has a huge influence on semiconductor behavior. As temperature increases, the bandgap energy decreases. This changes how electrons move and how photons are emitted. That's why laser wavelengths drift with temperature, and also why thermal management is critical in high-performance photonic systems. A table here compares materials like gallium arsenide, silicon, and germanium. Each material corresponds differently to temperature changes. This becomes extremely important in telecommunications, aerospace systems, sensors, and high-power lasers where stability is critical. Now we arrive at the core principle behind lasers. Under normal thermal equilibrium, most electrons prefer lower energy states. That creates a problem. Stimulated emission only works efficiently if more electrons are already excited than unexcited. This useful condition is called population inversion. To create it, we must pump energy into the system. In semiconductor lasers, this pumping is achieved electrically through current injection. In gas lasers, it can be achieved using electrical discharges. Once population inversion is reached, incoming photons trigger synchronized emissions. This creates optical amplification, and once amplification overcomes system losses, laser begins. This is the moment a laser crosses threshold. Real lasers are incredibly sensitive systems. One important parameter is threshold current. Below threshold, the device behaves almost like an LED. Above threshold, coherent laser emission suddenly dominates. Another important phenomenon is mode hopping. As temperature changes, the refractive index inside the laser cavity changes. The laser cannot continuously shift wavelength smoothly. Instead, it abruptly jumps between allowed resonant modes. This is called mode hopping. For precision applications like spectroscopy, telecommunications, and metrology, controlling these effects is extremely important. Laser engineering is not only about generating light, it's about generating high controlled light. Now let's switch perspectives. Instead of generating photons, sensors capture them. Modern image sensors rely on millions of tiny photodetectors arranged into pixels. Two major architectures are shown here. PPS sensors use one amplifier per column. APS sensors embedded amplifiers directly inside each pixel. APS designs dominate modern CMOS cameras because they allow faster and more integrated readout. However, the extra electronics reduce the area available for capturing light. To solve this, engineers place microscopic lenses above each pixel. These microlenses focus incoming photons into the active region. This dramatically improves sensitivity. Every smartphone camera today depends on this technology. The p-n junction is a fundamental building block of nearly all semiconductor devices. It forms when p-type and n-type materials are joined together. Because electrons and holes diffuse across the boundary, a depletion region naturally forms. This region contains an internal electric field. Even without external power, the field already exists. By itself, it is relatively weak. For efficient photon detection, we need stronger electric fields capable of rapidly separating charges before they recombine. And that leads us to reverse bias operations. When we apply reverse voltage to a p-n junction, several important things happen. The depletion zone expands, free carriers are swept away, and most importantly, a strong internal electric field develops. This field acts like a high-speed highway. When photons create an electron-hole pair, the electric field rapidly separates them and drives them toward the electric contacts. This prevents recombination and allows efficient detection. This principle is used in photodiodes, solar cells, and many imaging systems. These slides show the complete process of the photon detection. First, the photon enters the semiconductor and gets absorbed. Its energy creates an electron-hole pair. Next, the electric field separates the charges. Finally, the charges are collected at the electrodes and transformed into measurable current. This entire process happens incredibly fast. Modern sensors can repeat it billions of times per second. Every digital image, optical communication signal, or lidar measurement ultimately relies on this chain of events. Standard p-n junctions have limited depletion width. That means many photons can pass through without being detected. To improve efficiency, engineers developed the PIN photodiode. Here, an intrinsic or undoped layer is inserted between the P and the N regions. This dramatically widens the depletion zone. As a result, photons have a much higher probability of being absorbed. PIN photodiodes are widely used in fiber optics communications, imaging systems, and scientific instruments. They offer high sensitivity, fast response, and excellent performance. Sometimes capturing a photon is not enough. In extremely low light environments, the electrical signal may be too weak to measure. That's where avalanche photodiodes come in. These devices create an ultra-strong electric field inside the gain region. When an electron enters this region, it accelerates violently and collides with atoms. Those collisions release additional electrons. The process cascades into an avalanche. One photon can effectively generate many electrons. This internal amplification dramatically improves sensitivity. Avalanche photodiodes are used in quantum optics, lidar systems, deep space communication, medical imaging, and single photon detection. These are among the most sensitive optical detectors ever created. Thank you very much for watching. I hope this presentation helped demystify how lasers and optical sensors work and why they are becoming so important in modern technology. For quantum physics and semiconductor lasers, cameras, and avalanche detectors, all these systems are connected by one central idea: the interaction between light and matter.